Yep. So the section today which we are dealing with is the seismic analysis of the dam abutment. So this is the 5th session in the entire training series. So we completed the ground structure interaction in the very first session, and then there was a training webinar wherein we have created the entire model of excavation, and then we had a case study wherein the finite element analysis of heritage sewer using GTS and was discussed, and then followed by a training webinar on tunnel modeling. And now comes the seismic analysis of the dam abutment, so which I will be discussing it now. And the very last webinar of 2024 is on 10th of December, wherein we have a training webinar on ground structure interaction. So this is these are the topics, and let's start today's session on the seismic analysis of dam abutment. So these are the contents that I will be going through. So to give a brief idea about the project, a very brief overview, and then theory and modeling. So this theory and modeling is where I will be covering the damping. I will be covering the fluid structure interaction. So I will be covering the the interfaces, the meshing properties, and the boundary conditions. What can be used during the seismic analysis. So this will be the important part of all. And then during this theory discussion itself, I will be opening the software and I will show you the model, and then we can discuss. I will be discussing about how to create the infinite boundary conditions, how to apply the damping in the software, and how to apply the fluid structure interaction related modeling in this software. So that's the second and third part together. And here in the third part, I will also discuss about the results that were obtained from the analysis. And then very last, once the entire session is done, whatever questions that you guys have, I will be answering them. So let's talk about overview. So firstly, this is the project that was being constructed right now in India. So we have the dam abutment. So this is the wing wall, and we have a shear wall, and we have a backfill. So this is a backfill of once that is filled once the construction of the abutment is done. And over the length, along the length that I'm showing the direction in this direction. So this abutment or the wing wall will be transferred to an embankment, like an earthen dam, the joined earthen dam. But our major focus is on the stability of the abutment. So wherein you have a wing wall and you have a shear wall, and there is a backfill. And the major objective is as follows. So the objective is to understand the stability behavior. So when I say stability behavior, I'm talking about the tensile stresses, displacements, and of course, the factor of safety against sliding. In addition, we will also talk about the acceleration, so which I will be showing in the result interpretation tab. So because of the earthquake load, and because of the already existing the backfill and already existing the reservoir, so we need to consider reservoir for various load combinations. So in this situation, I'm considering load combination E, which I will talk about in the coming slides. So under this combination, how the behavior of the dam abutment is, and what are the tensile stresses, and how the displacements are obtained from this analysis. So that's the major objective. And of course, to calculate factor of safety against sliding. So this load combination E is considering the earthquake. Okay, so since there is an earthquake, so we have a change in the load with respect to time. So hence I'm calculating the factor of safety with respect to time. So this is the factor of safety versus time graph, and we are going to obtain this from this model. So let's jump into theory and modeling. So the first thing is geometry modeling. So I won't be modeling this entire model in front of you, but I will show you what it is there. So first thing is we have a very solid rock. So the rock is of a very good quality. And then we have a dam abutment, and it's basically wing wall, shear wall. So it is made of M20 grade concrete, and which is having 20 Newton per mm square of the strength. That's the compressive strength. And this is a backfill. So if you notice, we are not applying the backfill as a pressure onto the abutment, but rather we are modeling the entire backfill. So this is the backfill with soil properties, and we are going to apply this not as a load, but we are actually modeling it as a continuum. So the reason for this modeling of the backfill here, which is in interaction with the abutment, is to consider the effect of backfill due to earthquake load. So whenever the earthquake wave is passing from the base to the surface, there will be some amplification upwards, and that earthquake is having both positive and negative amplitude. And due to this, there will be some additional force applied by the the backfill onto the abutment. So hence, we want to consider the backfill as a direct model rather than applying as a load, applying as a mass or a load onto the abutment. So that's the idea. So the idea is to consider the effect of backfill and how it is interacting with the abutment due to the earthquake. And of course, in addition, we are also modeling the reservoir, not as an sloshing medium, but we are modeling it here as an mass. So I will show you how the mass was considered and what was the method that was considered to apply the mass onto the dam abutment. Okay, so let's actually go back to the model wherein I will show you the geometry. So here we go. Oh, I will like to share. Okay, now I think it is better. So this is the already modeled wherein you have the mesh and so on. So if I hide the mesh, and this is the geometry that was prepared. So let me hide the entire loading that was applied onto the geometry as well. So here we go. So this is the backfill, and here this is the dam abutment, and this is the solid for the foundation. So let's hide the solid for the foundation. And here this is the abutment, and along with the shear wall. So this is the shear wall where actually there has been a staircase modeled as well. So you can see the staircase inside the shear wall. So this has been imported from Revit, and then we have modeled the abutment, and then we modeled this foundation and the backfill. So just to make sure whether these all solids are in contact with each other. So let's see check the duplicates. So here, if you press apply, in this software, we have an option to check whether the solids are in proper contact with each other or not. So for that to happen, here we need to check the orange phases. So if you are finding any orange phases, then that means the solids are in proper contact with the adjacent ones. So here we go. The backfill here is in contact with the foundation, and it is in contact with the abutment. Similarly, the abutment is in contact with the foundation as well as the backfill. So just that's the basic check which we can do in order to understand whether they are in proper contact or not. So that's a basic overview about the geometry. So you have a lot of options to create this geometry. You have solid options, you have surface options, and so on. So you can simply import the surfaces, or you can directly import just like how I have done. So I had imported the entire shear wall. and then later on I had created the abutment on my one. So that's the idea, a very brief idea. So now, if we go back to the presentation, so let's talk about the next aspects, which is the meshing and interface definition. Okay, so here we can see the mesh. The mesh which that I used was the hexa-dominant mesh. So wherein you will have a lot of hexahedral elements. So the reason for using this hexahedral elements is to speed up the analysis. When we use hexa-dominant mesh, you will have a less number of elements, and because when there is less number of elements in the model, when there are less number of elements in the model, the time for analysis will be low. So the reason for considering the time for analysis is because we are running the seismic analysis, and whenever there is seismic analysis happening, there will be a lot of there is a huge possibility or for a lot of time steps in the model, and that may increase the time of the analysis. So hence, to reduce the time for analysis by certain extent, we went for the hexa-dominant mesh, so which is obtained by using the hybrid mesher in the software. And in the starting, I have said the objective is to consider the interaction. So hence, between the abutment and the backfill, an interface has been applied. Similarly, an interface has been applied between the abutment and the foundation. So the reason for applying the interface is, so let's say if the interface is not provided, then the abutment and foundation will be in rigid contact with the foundation, and the backfill will be in rigid contact with the abutment. So in whichever way the abutment is moving, the backfill will move in that way. Similarly, in whichever way the foundation is moving, the abutment will move in that way. So the reason is because they will be sharing common nodes, which will be like a rigid in nature. But the elastic modulus or stiffness of the rock and stiffness of the abutment is completely different. They are not of same magnitude. Similarly, the stiffness of the backfill and the abutment is not of same magnitude. So since the stiffness is different, the force that it can take, it will be different. And hence, there will be relative movement between the backfilling the abutment and relative movement between the abutment and the foundation. So to actually capture that particular relative movement, so basically the sliding phenomenon, so also the shear phenomenon, we need to model the interface. And again, to create this kind of interface, you have various options. So let's say you want to create the interface which will not transfer any tensile forces that is coming from the foundation to the abutment. So we have an option called full Coulomb friction, so which we will be modeling it now. So let's go back to the software, and then I will model the interface for you. So here we go. So firstly, let's go to the mesh, and this is the rock mesh, which is completely hexa-dominant mesh, and also the retaining wall, retaining soil basically. And then we have wing wall and the shear wall as well. So let's see what kind of elements are present in the model. So you can find around 58 or almost 60% of the model is of hexahedral elements. And then we have around 15% of tetrahedral elements. So the reason for forming the other elements is you can find there is a lot of curvatures in the wing wall. I mean, it is inclined, and we have some kind of curvature here as well, so near the galleries. So to cater to that kind of varying geometry, we need to have tetrahedral. And here in this software, this hexahedral elements will convert to tetrahedral elements via pyramid and pentahedron. So hence, you will be able to see all these elements present in the model. And due to this, you will have a less number of elements. So overall, we have 100,000 elements in the model. So now, let's see how to create the interface present in the interface in this model. So let's go to the interface option. So we have an option to create planar interface. So I will select the abutment and then foundation. So I want to have the interface between abutment and foundation, so which will help you out in forming the interface between the abutment and the foundation. So let's provide a reduction factor of 0.7. So the values of this reduction factor can be found in the help manual. So it depends on the material. So now the abutment is made of concrete and the foundation is a rock. So between the abutment and the rock, there are a lot of empirical research that was done, and you can find how much the reduction factor varies. So it generally varies from 0.6 to 1. So now I'm considering 0.7. So when you press apply, so the software will create an interface between the abutment and let's see. So here we go. Oh, I need to select mesh set. Sorry, I did a mistake. So instead of from element boundary, you need to select from mesh set. So then the software will be only creating interface between the selected mesh sets. So let's create 0.7 and let's apply. So now the software is creating interface by dividing the common nodes between the abutment and the foundation. So when you have this kind of interface, this is how it looks. So this is an element that is a new element that is formed between the abutment and the foundation. Okay, so let's see what material it is made of. It is made of material 7 here. So when you go to the material and see the 7, so you can find the normal stiffness modulus, shear stiffness modulus, and so on. Now, the tensile strength here is made to 0. So there won't be any transfer of tensile stresses from foundation to the abutment. So if the abutment is overturning, then it cannot take rock along with it. So that's the idea with here. So there will be a kind of lift happening at the heel of the abutment and so on. So now this is one interface which was created, and now we need to have an interface between the backfill and the abutment as well. So let's go to the interface and create a planar interface and go to the mesh set. So now this time it will be between abutment and the backfill. So you can use the similar value of 0.7, press OK, and then press OK. So now if I hide retaining wall and so on, so there is a new interface created. So let's see what is the properties. So it's the property of 9. So we can find that the stiffness is very small when compared to the stiffness that we have obtained a bit for the interface at the bottom. So the reason for this is the backfill is a soil, and the stiffness of the soil is very low when compared to the rock and the concrete. So depending on the stiffness of the soil, the normal stiffness modulus between the abutment and the backfill is low here. So this will be automatically calculated. And if you are interested in not transferring any tensile forces from backfill to the abutment, so you can even activate this option. So this option is available for you. If you are interested, you can go ahead with this. And then in the rock as well, these are the properties. And then the nonlinear properties wherein we have activated tensile cutoff as well. That means we are allowing the tensile cutoff, but the value is to 0. That means we are not allowing any tensile forces in that rock as well. So that's the idea. So now the entire meshing has been created, and also the interface between the abutment and backfill and abutment and the rock has been created. So now coming back to the presentation. So then next comes the boundary conditions. So the boundary conditions here is for both static analysis as well as the seismic analysis. So firstly, so let's consider static boundary conditions for the seismic analysis. So whenever you have the static boundary conditions like a roller or fixed supports, in that case, whatever the wave that is actually going through the medium, it will hit the boundaries and it will reflect back, and thereby there will be very huge amplification happening onto the structure. That means the forces acting on the structure will be very high. In a nutshell, the wave is a seismic wave. It is not the wave that is generated in this particular area, but it is happening that like wherever there was an epicenter, the wave is starting over there, and then it reaches this particular place, and then it goes away. So it's an infinite medium. So it's not the wave that is generated in this particular model or in this particular area. So because of this, we need to model an infinite boundaries, not the the regular static boundaries. So if you model, then there will be a lot of reflections of the wave, and that may result in more forces in the structures. And then that's the reason it is needed to model the infinite boundaries. So for infinite boundaries, we have free field elements. So there are two kinds of infinite boundaries. One is just absorbing the whatever the reflected, whatever the waves that are coming onto the vertical sides. And there are other boundary condition, which is actually modeling the entire infinite medium. So which is called free field boundary conditions. So either you can go for absorbent boundary, or you can go for free, or you can go for the infinite boundary. So that's for the vertical boundaries. And in the case of like base boundaries, it depends on the kind of wave that you are having. So I will talk about this in the coming slides. Firstly, infinite medium. So as I said, there are two kinds of boundaries, but one is the absorbent boundary. What happens over here is whatever wave that is generating that came at the base. So when it traveled to the top, basically the surface waves, when it traveled to the top. So the vertical boundaries, which is absorbent boundaries, will just absorb it wherever when the wave is reaching near the boundary. So it's not transmitting to the like infinite medium, but it's just absorbing it. Then there will be some, it might not be correct in all the conditions because of the following. So whenever you go for a free field condition, the wave is also transferring in the free field medium. So that means there is a propagation of the wave happening in the infinite medium as well. That should also be like considered in this condition, because that wave may transfer to the main model, and that may have some effect. But if there are some absorbent boundaries in this particular condition, it will absorb those waves, and it will not transfer to the main model. So hence, we need to consider waves that are going from this particular main model. We cannot consider the waves that are transferring from this main model to the infinite medium, but we need to consider the waves that are actually happening in the infinite medium and are transferring to the main model. So hence, the free field will be helpful, because it can it will not reflect all the waves that are generated in this main model, but at the same time, it will transmit the waves that are propagating from the far field or infinite medium here. So hence, is quite popular. And in this model, we are actually applying the free field boundary conditions. So I will show you in the model. And again, if you see, we have a backfill here. Okay, so this backfill, this is a backfill here, and in this backfill, you can see this is the entire vertical face of the soil. The soil cannot stand still over the entire length, I mean entire depth. So hence, we have created some spring conditions here. So this spring is also applied with the absorbent boundary as well. So the whatever waves that are transferring in the backfill will be absorbed in these conditions. So we are not considering to model the entire backfill along the length of the abutment. But here we are only modeling some extent, so that it will not fall off because of the vertical face. So we need to support this particular vertical face. Hence, to support this particular face, we are providing some stiffness and a damper to the spring. So we are modeling a spring in a nutshell. So to support the backfill, as well as to absorb the waves that are transmitting in this backfill when it comes to the boundaries of this backfill. So we are applying both the absorbent boundary condition as well as the free field condition in this model. And then this is how the absorbent boundary works. So for the absorbent boundary, so you will have the spring as well as damper. So this mass is nothing but the mass that is present in the element over there. So we created hexadominant mesh, right? So it will have some mass, and that mass will be given with the support of a spring and then the damper. So in this model, we are creating absorbent boundary, right? So for the absorbent boundary condition, we are applying it only for the backfill. So the backfill will have a mass, and that will be the spring and the damper. So this is the application of the absorbent boundary. So you can find the equations that are being considered by the software automatically. So software will consider the area of the element and then the modulus or stiffness applied to it and provide the spring automatically. And for the damper, we have this kind of equations that are considered. So you can refer to this in the Kramer earthquake engineering guide as well. These are the equations that are considered for calculation of the stiffness of the spring as well as damper coefficient for the damper. Then coming to the base boundary conditions. So here there are two kinds of base boundaries that we can apply. The first thing is we can apply the rigid or fixed base condition, and the other thing is to apply the infinite elastic half space. So which can be applied by the usage of a complying base or absorbent boundary in this software. So first thing is when to apply the fixed boundary condition or rigid base, basically. So whenever you have a within motion, firstly, let's say you will get the acceleration time history on the surface, right? So from the seismic hazard assessment, you have the PGA value, and that PGA will be applied with some time history, and you will have a time history developed. So that will be at the surface. So if you are considering the entire massless foundation, in that case, there is no need to deconvolute. Most of the times, because the rock is stiffer, it is okay to no need for deconvolution, and you can simply apply the surface wave that was the seismic hazard assessment wave that was created, and you can apply it at the base and you can run the analysis. But here in this analysis, we are considering it as a mass foundation, so the mass is considered. Because of it, there is need for deconvolution to be done in this particular case. So what we have done is, let's say we have this particular, let's say, seismic time history, which was obtained from the hazard assessment, and that time history of the acceleration cannot be directly applied at the base. So we need to first de-amplify it, so that let's say we are applying we are creating the depth of the model up to like around 60 meters. So we need to deconvolute the amplification until 60 meters. So here we are reducing the wave, the amplitude of the wave. Let's say it is like around 0.1 G here. Maybe at the bottom at 60 meters, it might be at 0.05 G only. So we need to deconvolute it, and that will happen based on the method called deconvolution. So it is nothing but the one-day ground response analysis. And again, at the base, let's say if we will have two kinds of waves after deconvolution. One is the within wave, and the other is the motion. So if it is a within wave, then we will be applying that within wave at the base of our finite element model. And particular within wave should be accompanied with rigid or fixed base. Okay. So if it is a within wave, it should be fixed base at the bottom of the finite element model that we are creating. First, suppose if you are considering the let's say outcrop motion at the base of the model. So if it is an outcrop motion, then we will be applying the outcrop motion at the base of the model, but it should be accompanied with a compliant base or absorbent boundary in the software. So here in this particular study, we obtained a within wave. So hence we are going to apply fixed base at the bottom of the model. So that's the idea. So the differences between within wave and rock outcrop motion is simple. So here we are in the outcrop motion. There will be both the upward and the downward propagating wave, and so we will be only considering the upward propagating wave in this condition, so here we will be considering only there will be like a kind of rock here, and then bedrock. You can consider bedrock, and there will not be any downward motion, and then hence we are only considering the wave, which is only upward propagating wave here. But in this situation, you might have both upward and downward propagating wave. So hence we are only considering upward, and since we are applying the we are considering the model, whatever the downward motion that is happening will be absorbed by the compliant base or absorbent boundary in this software. So it's just like eliminating the downward propagating wave here. So the reference for it can be applied, can be seen from this paper. So let's assign the free field condition, absorbent boundary condition, as well as the base boundary conditions in this software. So firstly, let's assign the free field condition. So here we have a free field, and the free field was already defined in this software. So you are considering the free field planar free field, and you have an option to create a free field motion. So let's consider the free field free field. This is what was created. Yeah, the free field, and there is here be completely free field in nature. So let's apply the free field. So you need to click on this, and then a new tab will be open. And since it's a planar interface, we'll go to the planar interface, and let's select all the elements on the on the vertical sides like this. Go to the top view and select all the all the element faces on the vertical side. You can see some elements have been selected. I'm just unselecting them. So this is unselect mode, and this is select mode. So now if you press apply, so you can see the entire free field element has been created. Okay. So the next thing is to apply the fixed boundary condition. Okay. So to assign the fixed boundary condition, you need to go to the static tab, and you have a constant here, basically the boundary constraint, and go to the advanced boundary, and you can actually fix the entire rotations and translation at the base nodes of your model. So you can say fix the bottom. And now we need to model the boundary conditions for the, we need to assign some boundary conditions for the sides of the backfill. So let's only activate the backfill. So this is the backfill, and here let's assign the absorbent boundary. So for that, go to the element and go to create tab, and here we have an option called other. So wherein we will be assigning ground surface spring. Where okay, so now like we will go to the first thing is to assign the stiffness of the spring, so which will be applied via several reaction modulus. And for seismic analysis, it's better to consider the modulus elastic coefficient as 2. So let's okay, you can select the entire mesh set and then press apply. So this is the stiffness which we are applying right now. And then once the stiffness is assigned, the next thing is to apply the damper. So here you have an option to consider damper, right? So let's select the entire mesh set again and press OK. So for each and every node in the model, the software will assign a damper as well as the stiffness of the spring. So if I hide the retaining wall, so you can see the damper and the as well as the stiffness of the spring which is applied. And the next thing is we already have created an interface, the free field. So since the free field is already here, there is no need to create a damper and stiffness. Basically, there is no need to create the absorbent boundary in this area, right? So I'm deleting the unwanted elements. So now these unwanted elements are now deleted. Then the next thing is to create, like I will just show you what is the stiffness and the damping coefficient that was created. So for each and every location, you will have certain stiffness, and then you will have damping coefficients as well. So the software will automatically calculate the damping constants as well as the stiffness at these locations. Okay, so now the model along with the boundary conditions is now prepared. So let's go to the presentation. So the next thing is the loading condition. Okay, so here let's go for the next option, which is the loading condition. So there are lots. This project is particularly like designed and being constructed in India. So hence the load combination according to the Indian Standard Code 2512/1984 has been considered. So there are lots of load combinations here. So load combination here, basically it's in the dry state. So once the model has been, once the dam has been constructed, but the reservoir is not filled yet. And we have load combination B, which is the normal operating condition. Load combination C, which is the flood discharge condition. And load combination D is with the combination A and earthquake as well. And load combination E is with load combination B, basically the normal operating condition with earthquake. And load combination F is the load combination C plus extreme uplift. And then load combination G is like extreme uplift along with the earthquake here. So that's the different load combinations. But here we are in this particular analysis, we are in this particular session, I'm only discussing about load combination E, wherein we have a normal operating condition load along with the earthquake. And for reference, we have different similar load combinations present in AS 5100 as well as ANCOLD guidelines. So for those who are dealing with the Australian projects, so you need to consider these load combinations according to the ANCOLD guidelines. So there is very subtle difference between Indian standard as well as Australian standard load combinations. So in Indian standard, the loads are applied as it is, and but in the assessment, like for stability of checks as well as factor of safety checks. So for the factor of safety against the sliding may vary for earthquake load as well as may vary for the normal operating condition. But here in the load combination as per ANCOR guidelines, so the factor load is applied directly applied onto the dam, but the factor of safety against sliding and overturning will remain the same because the loads are the ones which are factored here. But in Indian codes, it was the factor of safety that changed for different load combinations against sliding or so on. So yeah, so this is a very basic difference. And now in this model, we have considered the load combination E according to the Indian standard. So I will just show you the load combinations once during the application of the fluid structure interaction. So the next concept is the fluid structure interaction. So let's say we have a dam and we are considering the reservoir. So there are two ways to consider reservoir. One is to apply the entire reservoir as a mass, and the other is to create the reservoir completely. So in the case of added mass concept, we have two options, which is Westergaard's added mass concept, and the other one is C.N. Jager's added mass concept. In this particular analysis, we have considered the Westergaard method. So wherein this is the equation that is considered to calculate the forces acting on the face of the dam. And the major properties of this Westergaard concept is as follows. It is actually applied normal to the face of the dam. So if the dam is inclined onto the upstream side, then the force is also applied normal to that particular inclined face. Okay, and the load combination is parabolic in nature. So we can find this is the equation. So since we have square root here, of course the variation should be parabolic. And then it is very rigid in nature. So that means wherever the dam is moving, then the mass will move in that particular direction. I mean, the reservoir is moving in that particular direction because this is just an added mass and it's not the reservoir that was modeled. And there is no particular frequency for this mass which is added. It's a kind of applied load. So it's in rigid contact with the dam. So if your reservoir is deep and the dam is flexible, in that case, we will generally come to we will have the relative moment between the reservoir and the dam. Hence, we will have a lot of wave moments whenever there is an earthquake in the reservoir. So Westergaard equation will solve that particular purpose not quite well. So hence, if your dam is very deep and you have a flexible dam, in that case, it's better to model the sloshing fluid medium. That means you need to model the entire reservoir as it is. So we are modeling the reservoir using the element called sloshing fluid. So what it does is it allows the wave propagation in the water. So whatever the wave that is happening, so it will allows the wave propagation, and because of that sloshing, there might be additional force acting onto the dam. So we will have the waves that are created, and that may act some additional force onto the dam during the itself. And water is not rigid, unlike the assumption in the Westergaard's theory. And failure mode shape may differ from the added mass concept. So in the added mass concept, which is basically the Westergaard's equation or Jager's equation, we are applying the load as a mass, and it is rigid in nature. So hence the natural frequencies of the dam may differ when compared to the natural frequencies that you apply. I mean, that you obtained when you deal with the sloshing fluid. So this method is suitable when you are having a dam which is flexible and the reservoir is deep. And you also can account for relative moment between the dam, between the dam and the reservoir. So this is the basic idea. But in this model or in this analysis or in this study, we are considering Westergaard's added mass concept. So let's see how it works. For the easy purpose, I have applied all the loads on the geometry. So because of this, if I have any like a change in the mesh to be done, then I can simply delete the mesh or remesh it. There will be no need to reassign the loads onto the mesh because I'm applying it on the geometry. So here we go. So first thing is we have FRL load. So the depth of the entire abutment is like around 25 meters. So it's not deep dam. It's not a deeper dam. So here we have like FRL, and additionally we have hydrodynamic force, which has been applied based on the Westergaard's equation. So if I show you the hydrodynamic, yeah, here we go. So this is the parabolic equation that was obtained when we calculate it using the equation that was present in the slide that I had shown. So this is the parabolic load, Westergaard's parabolic load, and that has been applied all along the depth of the dam. And then we have applied the silt load as well, and both vertical silt load and lateral silt load. So the lateral silt load as well as the vertical one. And then we have applied the uplift pressure. So if I hide, yeah. So this is the uplift pressure applied at the base of the abutment, and all the other forces for other load combinations. So we have tailwater pressure as well, and uplift drains when drains are inoperative. So now the idea is to convert the entire hydrodynamic pressure, which I had applied, into mass. So here we have applied the hydrodynamic pressure, right? That was applied onto the face of the abutment and the wing wall faces here. But we need to consider that pressure which was applied as a pressure to a mass, because in dynamic analysis, it has to be mass which has to be considered and not the pressure. So we need to convert the entire load to mass. So we have an option called load to mass, and there is a new option called load direction. So in the newer version, we have this load direction. So because of this, you will be able to apply the mass in X, Y, and the Z direction of each and every node. So let's calculate the hydrodynamic added mass. So this is the pressure which we had applied. So this is the equation that we have selected here, and then press OK. So when you do this, you will be able to find the forces acting onto the dam like this. So at each and every node, so this is up to this extent, we have the FRL, basically reservoir level. And from this condition, you will be able to apply the, you will be able to have the hydrodynamic load. So now the beauty of this load to mass is you will be able to see the entire mass at each and every direction. So let's see the element table for that. So I will be only activating the load to mass. So at each and every node of the upstream side of the dam, you will be able to have the mass in X direction, Y direction, and Z direction. So if the faces are inclined in nature, in that case, you will be able to see X and Y and Z direction forces. If the faces are vertical, then you will be able to see only Y or X direction, basically horizontal or two horizontal directions, X or Y, and not the Z. So the reason to have masses in X, Y, Z directions are, so basically the mass is directionless. But for the analysis to happen, we are having the wave propagation in all the three directions, in X direction, Y, and Z directions, right? So since we have all the three direction waves being coming onto the dam at each and every node of the dam, so we need to have three masses. So if the X direction wave is coming, then the mass in the X direction wave will be considered. If the Y direction wave, then the Y mass. Similarly, if the Z direction acceleration is happening onto the dam node of the dam, then the inertia mass will be applied according to the mass which is given in the Z direction. So hence, it's always needed to convert the load to mass in X, Y, Z directions. So software will convert the entire pressure that was applied on the each node of the dam into X, Y, and Z directions. And for each component, it will be divided with the unit weight of water, which will provide you with the mass. Okay, so now the hydrodynamic pressure is also applied. Then coming back to the presentation, wherein the next concept of damping will be considered. So the next thing is damping. So in damping, in general, we consider it railing damping. And if you're not interested in railing damping, you can always go ahead with the hysteresis damping, wherein you can create the hysteresis model. You can use a hysteresis model present in the software, and you can provide the hysteresis damping. But railing damping is follows. So generally, this is the equation of motion. So this is the equation of motion, wherein you have a mass component, damping component, as well as stiffness component. And in the case of mass component, you are applying the mass in the form of unit weight. The software will automatically calculate the inertia forces. So when you're dealing with damping constant, so this is the additional component that is coming, which is the railing damping component. And the K is the stiffness component, which will be calculated based on the elastic modulus or shear modulus that you have given to the model. And this is the force applied. So here, for the damping component or railing damping component to be calculated, we need two coefficients, which is stiffness proportional coefficient and the mass proportional coefficient. And to calculate these two, we need to have the frequencies, which are fundamental frequencies, F1 and F2, and the damping ratios. So to calculate these fundamental frequencies, we need to run the eigenvalue analysis. But let's say this is for mathematical convenience which we are applying. The railing damping is for mathematical convenience. Since we cannot, we were not able to apply the damping as a material behavior previously. We used to apply the damping as a railing damping constant. So basically, an additional component has been developed. But due to the recent advancements in the studies, you can actually provide the damping behavior as a hysteresis behavior in the stiffness component itself. So what happens is, because of the hysteresis behavior, the stiffness will changes with respect to time. So hence, this matrix will get updated with respect to time, and because of this, the damping will be applied inherently. So that's for hysteresis models. So if you're not dealing with them, then it's better to apply it as a railing damping. And then it is needed to provide the damping coefficients by running the eigenvalue analysis. So in this model, we ran eigenvalue analysis with reservoir mass as well as without reservoir mass. So without reservoir as well as with reservoir. That means the reservoir over here is the added mass. In this condition, the added mass was also considered, and in this condition, the added mass was not considered. It's just the structure. So since the only structure has been considered, you will be able to find high frequencies here. So high frequencies will attract more forces onto the structure, and most of the times is conservative in nature. And with reservoir mass, you can see the frequency is a bit less. It's actually higher as well, but it's less than the reservoir without reservoir condition. So hence less frequencies. That means a less chance to attract more forces onto the structure. Hence, little bit less conservative when compared to this particular condition. But this is not the guideline which we need to consider, because if the frequency of the structure is almost matching with any of the frequency of the incoming seismic wave, then there might be a possibility of resonance and so on. So hence it's needed to thoroughly check the frequencies of the incoming wave and to understand the frequency of the structure with mass as well as without mass. Only then the decision of which frequencies need to be considered should be like I said. So in this condition, in this particular study, we have considered without reservoir mass because it is where we are having more frequencies, so which will attract more forces onto the structure. So I will show you the results of the analysis of eigenvalue. So firstly, this is one case wherein the mass of dam also considered. I mean, the mass of the reservoir is also considered. And there is another case wherein only the structure has been considered and no mass. Okay, that's my bad. I need to edit it and not copy it. So edit it. And you can see only dam and wing wall and the boundary condition at the base of the dam, which will be fixed support. And because of this, you will be able to see some frequencies obtained. Let's see the results. Okay, so in this case, I didn't save the results for the eigenvalue. But anyways, that were the frequencies that were obtained with and without a reservoir. So where we need to input those conditions of frequencies. So let's see the construction stage definition. So here we go. In the first stage, initial stage, we have only rock and the ground restraint and the self weight. Then in the second stage, we have the dam, the backfill, as well as the dam, basically abutment, wing wall, and the shear wall for the staircase. And then in the third stage, we are applying the entire load for load combination E, wherein you have a mass for all the loads that were applied, as well as the hydrodynamic mass. You need to define the time steps according to the loads that were applied. So in this condition, we have considered the analysis for 11 seconds, and the result for every 0.01 step will be saved. So hence the time increment is of 0.01. Then for the damping, we need to go to the analysis control. And here in the damping method, you can provide the frequencies. So here I have provided the frequencies for without reservoir mass, wherein the frequency is higher when compared to the with reservoir mass. So it's 19.23 and 24.22. So this is what I have considered for the analysis. And yeah, so this is a design-based earthquake for load combination E. So you can see that the same design-based earthquake was applied in X direction, Y, and Z direction. So the scale factor for X and Y conditions are, as you can see, this is the scale factors. But for Z condition, it will be different because this is what the coefficients that we will apply from the hazard assessment as well as the guidelines. So this is the vertical movement. There is the vertical time history for acceleration. So we have increment of 0.01, which was, that's the reason we have considered the increment as 0.01. And yeah, that's all. That's the definition of damping as well as the definition of the construction sequence. And that's an idea about the theory, and we will go for the result interpretation now. I think I have already shown the demonstration, but we'll see the results as well. So firstly, we have two conditions. We will see the tensile forces as well as factor of safety against sliding. And okay, in addition, we also need to see the acceleration. So let's see the factor of safety against sliding at first. So these are the equation according to the Indian standard 6512. Wherein the factor of safety against the sliding is nothing but the resisting force upon the applied force. So the resisting force, where we can get it from the interface result, and this is the cohesion component, and similar equation. So this is also resisting the force upon the applied force, so which we will be calculating it from the software directly. So firstly, so when we go to the analyzed file, so I will only activate the interface at the bottom of the abutment. So this is the interface that was obtained at the bottom of the abutment. So here we have this is a planar interface. So there is a possibility for a movement of the dam in upstream to downstream direction, as well as sideways direction as well, because we have a backfill that was present. And since backfill is interacting with the abutment, there might be a possibility for the movement in this direction. And because of the reservoir load, there is a possibility to move in the upstream to downstream direction. So hence, it's needed to take both horizontal and friction as well as normal forces here. So to extract it, so we need to go for the interface stresses. So we have three components: normal force, that means normal to the element axis, and then the tangential, which are basically the friction in y direction as well as x direction. So let's consider the normal. So you need to select all the elements, and then according to the node, and I want to only give it in the time step and not the maximum, minimum, and absolute steps. So let's yeah, anyways. So when you click on table, the software will show you the element, XYZ components, and you can find the normal force for normal, the normal resistance in X direction for each, and this is the X direction is nothing but the local axis direction. So this is a normal force. That means from foundation to dam direction, not to the like upstream to downstream. Basically, it's not the lateral direction, but it's a vertical direction. So for each and every element, you will be able to see some normal forces. Similarly, let's extract the forces in the stresses. So we are now extracting the stresses, not the forces. So when you click on a table, the software will show you the tangential stresses in the local y direction. Similarly, you need to extract z direction as well. So now, so firstly, I have copied all the results of the normal forces into the Excel sheet. So you will see a lot of forces here. So I will just give you an idea. So this is the element. So we have a number of elements, different elements, because there were many number of elements in the interface. So for each and every element, we have obtained the normal forces. So one element, two elements. So element direction is along the row direction, and the column direction. Along the column direction is the element, and in the row direction, basically we are having the time steps, or nothing but the time, like we have considered the analysis for 0.01 time increment, right? So we have obtained like around more than 1,000 time increments. So yeah. So these are the stresses. We need to convert these stresses into forces. Okay. So if So we need to consider these entire stresses for each and every element to the forces. In this particular model, I have considered the mesh size as 1 meter. So hence, we are able to get the forces equal to stresses, because stresses applied by 1 meter by 1 meter in the area direction is nothing but the same force value. So hence, I have summed up the forces of the entire interface elements, which is nothing but the whole normal force in acting onto the abutment. So this is a force in at 0.01 time step of the earthquake. Similarly, for along the vertical direction, we have various time steps and hence various forces. So basically, I have summed up the forces for each and every time increment for the entire interface elements. Similarly, we need to do the same for the tangential forces. I mean, the sliding forces. This is the sliding force in local y direction and sliding force in local z direction. Then we need to copy the sum forces into this particular case. So we have this is the normal force, basically the normal resistance or resisting force, and then we have sliding force in y direction and sliding force in z direction. And since the waves are transferring in x direction as well as y direction, so it's better to calculate the total sliding, which is nothing but the square root of sum of the sliding forces in x and y, z and y directions, local z and local y directions. So this is the driving force, and this is the like resisting force. And based on the factor of safeties that I had shown you in the slides, you need to calculate according to the sliding force as well as the normal force. So the denominator is nothing but the driving force, and the numerator is the normal force or resisting force. So this is without cohesion term. And if you are considering the cohesion, of course, there will be more factor of safety. So if you see the term here, the first term is nothing but according to the force, normal force, and the second term is with respect to the cohesion component. So if you want to consider the cohesion component, then we can consider that as well as a resisting force. In the same ANCOL guidelines as well, you have the cohesion component. So now we have the factor of safety is calculated with cohesion and without cohesion as well for each and every time step. So if you draw the graph, yeah, so x-axis is the time and the y-axis is the factor of safeties. So according to the Indian standards, the factor of safety should be greater than 1 for load combination E, wherein all the static loads plus the earthquake has been considered. So you can see for each and every time step, the factor of safety is greater than 1. At some time steps, you can see the driving force is much less than the resisting force. Hence, the factor of safety has reached around 8. But overall, the factor of safety is around the average is like around 4. But this is the factor of safety time history. So you can draw this kind of graph for every load combination. Then, so here we go. This is the acceleration. So let's draw the acceleration in this particular analysis. So I would like to see how much the amplification might have happened. So we'll go to accelerations. And I will see the total acceleration because we have accelerations applied in x, y, and z directions. And so the force or the acceleration time history at the base nodes will remain the same, but at the top node is the amplified one. So let's draw the graph. Oh, sorry, we need to consider according to the step. Okay, so now right click and click on graph. So in the x-axis, we are considering the time steps, which is 0.01, 0.02. Hence, it's the step value because it's step value here. In the y-axis, we are considering the accelerations in at the base of the dam model as well as the top node of the shear wall. So this is how the amplification is. So you can see the amplification had reached at around 4 on the top node of the dam. And at the same time, the peak acceleration which was applied at the base of the model is somewhere around 2. Okay, so when you consider the amplification, you can see 4 point, let's say 2, or you can simply say 4 divided by 2. So the amplification has been like around 2. The factor of safety is the amplification factor is 4 divided by 2, which is 2. Like it's a general thing which I'm saying, but you can take the average one and consider the amplification factor as well. So this is for acceleration. Similarly, you can get the displacement time history, or as well as the backfill time history. So you can see the backfill is changing here. I mean, the backfill pressure is being changing because of the wave that is generating. The pressure applied onto the abutment because of the backfill is changing with respect to time. So to consider that, we have went for the interface behavior. Otherwise, there would not be no need to go with the interface behavior had you applied the backfill as a pressure load. Okay. So yeah, the amplification has been satisfied. The factor of safety has been satisfied, and even tensile forces has been satisfied. So tensile stresses. So let's see the tensile stresses in the model. Let's hide everything and accept the abutment. So let's go to the absolute force condition, and let's activate principal stresses. So the principal stresses are the ones that will help you out in understanding the tensile stresses in the dam. The positive value represents the tensile stresses, and the negative value represents the compressive stresses in the principal stresses. So in this case, we can see the maximum tensile stress is of like around 0.8, but that is only at the very minute area, so you can actually ignore it. So based on the US Army Corps or any guidelines such as ANCOLD or Indian Standard Guidelines, you will be able to calculate the maximum allowable tensile stress. And if that tensile stress is greater than this value, then your dam is safe. But let's say if the obtained tensile stresses is greater than the allowable tensile stress, then maybe the possible reinforcement at that particular area, or maybe you need to change the design of the model so that the tensile stresses taking onto your dam will be lower. So this analysis will help you out in understanding the tensile stresses, as well as obtaining the factor of safety against sliding, as well as considering the amplification because of the earthquake wave. So one analysis wherein you can see all kinds of results for the stability assessment, as well as consideration of factor of safety calculation. So yeah, overall this is the entire study that we had done for this particular project. So if you have any questions, please go ahead. You can write to me in the questions tab. And for those guys who want to go out of the webinar, yes, you can go because I'm done with the session. So yeah, now we are open for questions. Please write to me in the questions tab. And thank you for attending this session. So I will answer the questions now. And yeah. Okay, there is one question from Mr. Rahman. What is the difference between plane and shell interface? So basically, the planar interface is applied between two solid elements. It's a kind of surface interface. But when you are applying the shell interface, it's between two shell elements. That means between two shell elements, it's the line that is forming. I mean, the contact is a kind of line. So between those two lines, you will be having a line interface or nothing but the shell interface over there. So between two shell elements, if you want to apply the interface, it should be shell interface. But when you're dealing with the interface between two solid elements, then it has to be planar interface. And there is one more question from Mr. Rahman as well. How do I apply the Westergaard's method manually on the sloping earthen dam In 2021 version, yeah. So if you are using 2021 version of the software, then manually, if you need to apply, you need to. So I have shown you the element table, right? So you can copy paste all your Excel values onto this element table. Then you'll be having the mass components in X, Y, and Z direction. So let's say you have calculated the masses along the depth in an Excel sheet. You can simply copy it and then paste it in the element table that I had shown in this session. So that there you will be able to have the mass getting updated. So that's a manual way. But in the current version, the software can do it automatically. And there is one question from Jenny. Just wondering why we need to build construction stage. What's the consequence if you don't model construction stage, like what you did? The construction stage is important. The reason for that is the material non-linearity. We are considering the material as a plastic material in this model, which is the molecular model that has been considered. So what happens is, let's say, in the elastic region of the model that you have considered, the behavior would be the same if you apply it in the construction sequence, or if you apply it in the construction without construction sequence as well. But let's say if your model is reaching the plastic state just because of the static load that you had applied, in that case, there might be behavioral change in the material of the rock as well as backfill as well as abutment. So if your material is reaching plastic state before the earthquake, then in the earthquake or in the plastic state, the analysis will be carried out, and there will be quite a lot of difference. And also, there is one more difference. Let's say in the first stage, you have the only rock, but in the second stage, you have the dam. So because of the dam weight, it will deform onto towards the upstream side, right? So onto the deformed shape, the load, hydrostatic load, all those things will be applied, but not onto the original shape where the loads were applied. So there will be difference in the stresses because the force is now applied onto the deformed shape and not onto the like a original shape to which you have modeled. So hence, it's better to consider the construction stage always, because you want to consider the deformed condition as well as the material nonlinearity and geometric nonlinearity. So if you are dealing with such kind of situations, yeah, it's better to consider the construction sequences. There is one more question from Jenny. What skill you use to ensure the mesh size is to be 1 meter when you calculate the normal force and sliding force? So you have an option to calculate the size of the element. So you have X, Y, Z coordinates of each element. But mostly what I have done is I have imprinted the entire base, almost the entire base with 1 meter lines. So when you're doing that, we are forcing the software to create 1 meter mesh over there. But let's say it's very difficult to use 1 meter mesh size, and your program is, your model is challenging, and there are lots of shear zones and all these conditions. So in such cases, it's not possible to go for 1 meter mesh size. This relatively simpler model, and I went for 1 meter mesh size. But if you're dealing with a complex model where it's difficult to go with the 1 meter mesh size, then it's okay to go with any kind of mesh size. Once the analysis is completed, we need to like obtain the area of each element. So you have an option to calculate the area by using the XYZ coordinates that were obtained from the element table in this software. And then once those are calculated, you'll be having the area, and that will be multiplied by the stresses to find the forces and so on. So yeah, you can obtain the coordinates. Basically, from them you will be having area, and then you will be dealing with the stresses, stresses from the interface. Yeah, so silt load, there is one question. Can you explain about silt load? So silt load has been applied based on the Rhein theory here. So onto the upstream side of the dam. So if you know the unit weight of the silt, right, or you can consider the unit weight from the already existing the silt related unit weight, which has been there. I mean, in the literature. So if you know the depth of the silt that was applied onto the upstream face of the dam, so that depth all along the depth, you can provide maybe triangular load combination. I mean triangular load variation. So 0 at the top of the silt and unit weight multiplied by height at the bottom. So you can do apply the silt load accordingly. So it's like Ranikine or Coulomb's theory, which you can go ahead with while applying the load. So yeah, those are all the questions. I hope you had enjoyed the session. So if you have any more questions, you can drop me in the questions tab. Otherwise, we can conclude the session. So once again, thank you everyone for attending the session. So meet you again on 10th of December. Until then, have a great time. So I'm ending the webinar for everyone.